Portal was one of the standout games of 2007, and its 2011 sequel built upon a solid mechanical foundation, resulting in a highly polished game and, more importantly, one of the most talked about game mechanics ever. Last year on my website, I wrote about how I got portals working in Unity, and recently I upgraded the project to Universal Render Pipeline. It's time to grab our Aperture Science handheld portal devices and think with portals. I'm using Unity 2019.4, but this project should work on later versions of URP. Portals are deceptively complicated to implement because there's so many moving parts, so I'm going to break down the effect into rendering, then shooting new portals, and then throwing things through them. I'll be skimming over some details that don't really fit into this video, so download the project source on GitHub if you want to read through the code yourself and play with the project. I've definitely had a ton of fun placing down portals. If you want me to cover more complicated game effects like this one, these tutorials take a lot longer than my others, so the best way to encourage me is to subscribe to my channel, share this video with your friends, or support me on Patreon. The more people talking about my work, the easier it is for me to get stuff out, so spread the word. Let's go over all the moving parts required for rendering. No pun intended. Portals go in pairs, and for each portal within the pair, we'll position a virtual camera behind the other portal using some fancy maths to take a snapshot of the scene, and then save that to our render texture. We need to do that for both portals before the main camera renders. Then, when each portal surface is drawn by the main camera, we can sample its corresponding render texture in screen space to pick the bits intersecting the portal. The maths for positioning the cameras gets a bit tangled when we factor in portal recursion, seeing portals through other portals, so let's see how that works. I've opened up a script called portalcamera.cs which is attached to the main camera. We'll need to import a few namespaces that are related to rendering because we need to use a couple of fancy new camera rendering callbacks, and then we need a handful of variables. Most obviously we're going to reference both the portals, so for that I've used a 2-element array. The portal camera, in other words the virtual camera that we're going to reposition, comes next. It's important to note that this camera is disabled, so it only renders when we tell it to. Next, we'll define the number of recursive iterations. We need to render once per portal per iteration, so don't make this too high unless you're making a portal PowerPoint. I find that 7's a good number. We need to create one render texture per portal, so we'll create them in Awake and reuse them each frame. Finally, we'll store a reference to the main camera because we need it for our calculation later. We'll use getComponents to grab that in Awake. In Start, which runs after Awake, we will assign the two render textures to each portal's renderer. In the built-in render pipeline, we used to have access to methods such as onPreRender and onPostRender, but they've been deprecated in the new render pipelines. Luckily, Universal Render Pipeline gives us access to callback events which are fired at specific stages in the rendering loop, such as immediately before camera rendering. That's convenient! In onEnable and onDisable, we will subscribe and unsubscribe from the begin camera rendering event by register our update camera method. The update camera method is passed a scriptable render context and a camera. That camera is just the main camera, and the scriptable rendered context contains a bunch of state and lets us issue drawing commands and cull objects, and you know what, let's just move on before I go down this rabbit hole and end up explaining how your GPU's calls work. We won't render if either portal hasn't been placed. Then for each portal, we'll make sure it's visible before rendering, and then we'll set the virtual camera to render to one of the render textures. We need to render the deepest iteration first, and then the next deepest, and so on until we render the base iteration. Then we'll repeat that for the second portal. The magic happens inside the render camera method. In this method, the in portal is the one being rendered onto, and the out portal is, well, the other portal. We need to reposition the virtual camera so that the offset between the virtual camera and the out portal from behind is the same as the offset between the main camera and the in portal from in front. We start by placing the virtual camera at the main camera's position. We can then use inverse transform point to convert the virtual camera's position from world space to the in portal's local space. Then we'll rotate it around the y-axis by 180 degrees to move it from in front of the portal to behind it. Now the camera is in the correct relative position. We'll set the virtual camera position back to world space using transform point but this time using the out portal. We'll do a similar process of the camera's rotation using quaternion.inverse. We'll then repeat that whole process if this is a deeper iteration. The camera is now positioned correctly, but we need to talk about clip planes. If we just take the screenshot now, we will end up rendering the wall behind the portal and the portal surface will be rendered incorrectly. This is the part that took me the longest to figure out originally. We can't just set the virtual camera's near clip plane like usual because we'll end up cutting the camera rendering in the wrong place. We need to cut it along the plane that the portal surface lies on. We need what's called an oblique projection matrix. Unity provides a method to do this, but first, we need to calculate that clip plane in camera space. We can define the clip plane easily enough in world space by defining a plane object, which Unity can do, and then converting it into a vector 4 in normal distance format. Don't worry if you don't understand this maths, because we're only going to need to do it once. To convert to camera space, we can take the inverse transpose of the virtual camera's world to camera matrix and then use that to multiply the world space clip plane. Now that I've almost exhausted my allowance of maths terminology for 2021, we can pass that into the calculate oblique matrix method and assign that to the virtual camera's projection matrix. Finally, we can take the screenshot! When we take the screenshot, what's the portal shader doing? It's actually remarkably simple. All the shader needs to do is sample the virtual camera's render texture in screen space and output the texture's colour. This next part will assume that you've done a bit of shader coding before. Creating shaders with the universal render pipeline is very similar to creating shaders with the built-in pipeline, but instead of writing shader code within CG blocks, we use HLSL blocks. CG is a deprecated shading language which cross-compiles to other languages, such as HLSL, but now we just use HLSL directly. The URP's specific shader packages we import are a bit different too. We can also specify which render pipeline we are using with a render pipeline tag and use other subshaders for other pipelines, but we don't really need to worry about other pipelines here. Another special thing we're doing here is adding a stencil because the portal surface and the portal outline meshes intersect with each other, and I just use a stencil to cut out the portal surface from the outline object. We set a stencil value of 1 here while drawing the portal surface, and when it comes to drawing the coloured outline, we discard all pixels that have this value. Inside the vertex to fragment struct, we can declare the screen position UVs in the first texture coordinate slot. In the vertex shader, we'll use the transform object to hclip function to convert the vertices from object space to clip space. Then we can convert to screen position using compute screen pos. In the fragment shader, we divide the XY components of the screen pos variable by the W component in a step called the perspective divide, which gives us the correct UV coordinates for screen space sampling. Then we just use the text2d function to read the main texture using those UVs. That's all there is to it. Now that we can render portals, let's talk about placing them. The basic idea here is to fire a raycast from the centre of the main camera forwards and position the portal at the intersection with the wall. We can rotate the portal so that its normal direction points inwards towards the wall, but we also need to correct the position so that the portal objects don't overhang or intersect a wall. And we might need to add the ability to shoot new portals for an existing portal. Let's delve into the portalplacement.cs script. For this script, we need a reference to the portals, for which I made a portal pair upper object, a layer mask, which will use the raycasts, a reference to the crosshair, which we'll skip over during this tutorial, and a reference to the camera controller, which contains the camera's target rotation, which we'll use for orienting the portal correctly. In awake, we'll get a reference to the camera move components, and then an update, we'll call the fire portal method. Depending on whether we press the left or right mouse button, we'll fire a blue or orange portal respectively. The fire portal method takes in the portal we're trying to fire, the raycast position and direction, and a maximum distance that the raycast will propagate for. We will immediately perform the raycast and retrieve the raycast information inside a raycast hit object. Then, if hit.collider is not null, that means we hit something. We'll skip over the case where we hit a portal for now. We will calculate the orientation the portal faces based on several factors. The right hand direction is based on the camera's facing direction, and the forward direction is the negative surface normal of the point the raycast hit. We can then use the cross product to calculate the up direction, although it will be the wrong way round, so we will negate that. Then use that and the forward direction as parameters to quaternion.look rotation. Once we know the position and orientation that we want the portal to be in, we can call the placePortal method, which we will delve into shortly. Once it's placed, we will update the crosshair to show which portal was placed. Now that's dealt with a scenario where we hit a wall. What about when we shoot through a portal? Portal, the video game, doesn't let you do this, although Narbacular Drop, the demo on which Portal is based, does. We'll consider the portal we shot to be the in portal, and the basic idea is to start a new raycast from the out portal at the correct position and rotation with a shortened maximum distance. If we allowed an infinite distance, then this raycast could propagate forever through two portals facing each other, which would crash your game. Once we've got a reference to the in portal and out portal, we're going to use the same approach as we did when positioning the virtual camera. We'll use inverse transform point and transform point on the hit point plus a small offset so that the new raycast doesn't start inside the out portal. For the direction, we use inverse transform direction and transform direction on the in portal and out portal respectively. Then we subtract the length of the raycast between the origin and the in portal hit point and call fire portal again, then return immediately. The process for actually placing the portal is quite finicky. We need to position the portal where we've calculated, but we might need to make adjustments to make sure that the portal doesn't overhang on the edge of a floor or intersect with a wall. In the portal.cs script, the most relevant member variables are the placement mask and test transform. The layer mask named placement mask is used for raycast testing to check for intersections and overhangs, and test transform is a temporary transform we use for those tests. We also store the wall collider for a later step in which we deal with warping through portals, and we use isPlaced to determine whether the portal has been shot onto a surface. The portal's collider and renderer are used for small fixes later, and both are assigned in awake. If the other portal hasn't been placed yet, then we need to turn off the renderer so that we're not just rendering a huge black oval. We do that in update. In the placePortal method, we position the test transform at the desired spot with a tiny offset away from the wall, and then we may immediately perform checks for overhangs and intersects. Once we've done those fixes, check overlap, make sure that they worked, and if so, we'll actually place the portal properly in the fixed position. Otherwise, we're probably in a scenario where we shot a wall, but there's not actually enough space for the portal to exist, so we return false. Fix overhangs works by testing the top, bottom, left and right edges of the portal rectangle and checking those points are inside a wall. If any one of those fails, then we'll raycast towards the middle of the portal from that point and shift the portal in that direction by the raycast distance to move it back onto the wall. Fix intersects is similar. It tests from the center of the portal, offset away from the wall slightly in the four cardinal directions parallel to the portal. If those raycasts find a wall too close, it means that the portal intersects the wall, so it will correct the position by moving the portal away from the wall. The check overlap step is a sanity check to make sure the corrections worked. For example, the portal is 2 meters across in the x direction, so if we try and place it on a surface which is only 1 meter across, then despite the corrections, we would end up trying to place the portal in an invalid position. This method is tedious to explain in detail, so to cut a long story short, we use physics.overlapBox to make sure we don't intersect a wall, but we make an exception to allow the new portal position to overlap the old portal position. Then we use physics.linecast to make sure that all 4 corners of the portal's bounding box overlap a wall to avoid overhangs. With all these steps in place, we can fire portals and it will correct or prevent those shots where necessary. In this example, I'm trying to shoot this thin section of wall and it won't allow me to fire a portal here. The final part of the puzzle is portal travel. When an object crosses the portal boundary, we need to warp it to the other portal and preserve its speed and direction relative to the entrance and exit portals. We also need to create a clone version of the object to instantiate at the exit portal while the object travels through the entrance portal. Each object that can warp has a portalable object script attached, including the camera controller, which is a special case, so it needs to inherit from portalable object. Let's go over the variables. First, there's the clone object. Next, we keep track of how many portal triggers were inside. I can't remember exactly why I made this a counter rather than a boolean, but I'm sure there's a good reason. We need a reference to the pair of portals being travelled through and references to the rigid body and collider because we need to modify the velocity and the collision layers on the object. Finally, I cache a 180-degree rotation. You could go back and include that on any of the other scripts that use a 180-degree rotation too. On Awake, we need to create a brand new clone game object and give it the same mesh filter and mesh renderer properties as the primary object. We won't add colliders or rigid bodies to it because its position and rotation only mirror the main object through the portal. We also cache the collider and rigid body components here. In Late Update, which runs after the portal rendering and physics updates, we will check whether the clone and both portals are active. If so, we use the same inverse transform point and transform point trick that we've seen before to position the clone through the portal, and we do the same for its rotation using quaternion.inverse. Otherwise, the clone is teleported to a far away location. This happens if the main object is inside a portal trigger, but the exit portal isn't active. This script has a method called setIsInPortal, which is called when the object enters a portal trigger, which disables the collisions between the object and the wall the portal is on, using physics.ignoreCollision. Portals have a collision frame around them to prevent objects clipping through the side of the portal, which would look odd. There's a corresponding method called exitPortal, which is called when the portalable object leaves the portal trigger, which reinstates the collision between the object and the wall by using physics.ignoreCollision with a false parameter, and disables the clone if the object is no longer inside any portal triggers. Finally, portable object has a method called warp, which uses inverse transform point, quaternion.inverse, inverse transform direction, and the relevant opposite processes to teleport the object, rotate it correctly, and change its velocity direction respectively. At this point, the portalable object will actually trigger the opposite portal's trigger, so we need to swap which portal is the in portal and which is the out portal. Warp is called when the object goes behind the portal surface. Back in portal.cs, onTriggerEnter checks if the object that triggers it has a portable object script attached, and if so, it gets added to an internal list of portal objects and setIsInPortal is called on the object. onTriggerExit naturally does the opposite. When a portalable object leaves, it's removed from the list and exitPortal is called on that object. What do we do with that list of portal objects? In Update, we iterate through all of them, and using inverse transform point, we can check if its Z position is less than 0 relative to the portal. In other words, the object is behind the portal, and if so, we call warp on that object. There are a few other loose ends to tie up, but with the techniques we've discussed, you should be able to get realistic portals up and running in Unity's universal render pipeline. You can find the code on GitHub, where you'll find bits not mentioned in this video, such as what happens when the camera travels through a portal. All I ask is that you don't try to question me on what happens when you send one portal through another. Enough people have had breakdowns trying to answer that philosophical powder keg. A big thank you to all of my Patreon supporters for making this video possible, particularly those whose names are on screen right now. If you want access to exclusive polls, ad-free articles, and early content, give my page a look. Thanks for watching.